Hello, the topic of our seminar today is speeding up Python code with Numba. Here's my contact information if you have any questions after the seminar. So let me start with an overview. Python is a language widely used in scientific computing. It's highly popular. The main reason for its popularity is that it has easy to use syntax, which permits fast code development. So if you are a scientist, a researcher, and you want to test an idea quickly, you can write a Python code much faster than you could write the code in another language. However, Python has a problem in that it is an interpreted language, so it can be much slower than a compiled language. And by much slower, I mean hundreds of times slower. So this can be a concern. If you're doing something simple, like running your program for only a few seconds to analyze some data, that's not a big issue. But once you start to analyze a lot of data, do a lot of computing, especially once you move to a HPC cluster like we have at the Alliance, this becomes a concern, because if your program is running hundreds of times slower, then instead of getting results in 1 day, you will get a result in 100 days. And that will slow down your research by quite a bit. So there are various ways to address this issue in Python. So clearly one possible way would be to just abandon Python and write your code in a compiled language, but that is time consuming. You have to learn this compiled language. You have to become good at it. You have to rewrite your code. So that's possible, but it's not really a viable approach to get a speed up quickly. So a way to get a speed up quickly is to get the computer to convert your Python code into compiled code automatically. And this is the approach which Numba takes. It can take your code and with just a few, hopefully with just the additions of a few lines of syntax, the code will be converted to compiled code, and your Python code will then run much faster. And this seminar will sort of show you the difficulties of doing this and the issues involved. And you don't have to convert your whole code in this way. You can just focus on the functions which take the most time. So you can profile your code, find out the few functions where it's spending the majority of the time, and just convert those to compiled code, and you'll get the code running much faster. So I don't really have time to talk about profiling in this webinar, but you can find various resources online for how to do this. Now, the important point here is that only a subset of Python is currently supported by Numba. So you cannot just take any Python code whatsoever and use Numba on it to speed it up. Unfortunately, there are some features of Python which are not currently supported, and I'll talk about those. So hopefully, as Numba continues to be developed, this subset of support in Python will continue to grow. So just a few words about how you can actually install Numba and run the code examples, which I will show here. These are instructions for the Alliance clusters, but installing on your own home computer would be quite similar to this. So we load the necessary Python module, we initialize the virtual environment, we source it, and then we pip install Numba. And that's basically all you need to do. And then you run this once, and when you want to use Numba afterwards, you just run the source command, and then you run Python with the code that contains Numba syntax, and that's all that's required. So what is Numba syntax? Well, it's really quite easy, because often all you need to do is you need to add a simple decorator in front of the function that you want to compile. So you identify the function in your code where the code spends a lot of time. And if everything goes well, and if this function doesn't contain any code that Numba has trouble compiling, if you just add those 4 characters in front of the function and you run your code, Numba will compile the function. So the code will run just like it usually would, but it will hopefully run much faster. Now, there is a switch to the JIT decorator, no Python equals true. This forces Numba to compile everything. So without this decorator, Numba tries to compile code, Python code, but if it finds a part of the code which it doesn't understand how to compile, it will just leave it as Python interpreter code. So this means that this will always work, but sometimes your code will not actually be speeded up. So by adding this flag, you are forcing Numba to compile everything. in that you will actually get an error and your code will not run if something doesn't compile. And this is a safer approach because actually you want to be sure that everything is speeded up, that everything compiles. So by selecting this option, you can be more rigorous about making sure that your code is faster. And because that's used so often, there's even a shorthand option, which I will be using here, just NJIT. This means use just-in-time compiling. That's what JIT stands for, but compile everything. So basically, if everything goes well, you just add this line. And if there are no warnings or errors when you run the program, that means that Numba was able to compile everything and your program is hopefully running much faster. So in the first part of this webinar, I'm going to show cases where everything works like this. Everything works great. There are no issues. The code just compiles. And then in the second half, I'm going to show you a few examples when you actually do have issues. Numba cannot deal with some syntax. And I'll give you some ideas on how to change your program to make Numba work. So Numba actually compiles your function the first time it is called. So the first time you call a function with a Numba decorator, it will be a little bit longer than the subsequent calls because the function actually has to be compiled. So keep this in mind if you're timing code and trying to benchmark performance. So always run this function at least once, so the compiling step is done, and then actually start running it again to do your timing. Now, if compiling takes a long time, there's a pre-compile mode in Numba where you can compile everything before you start running, but I'm not going to cover it here, but just be aware that it exists. So Numba will figure out all the variable types of your function arguments when you call your function. So let's say when you define, remember that Python doesn't have explicit types. So when you declare a function, which let's say has argument x, y, you don't specify what the types of these arguments are. So what Numba will do is when it calls your function for the first time, it will see what is the type of x and what is the type of y, and then it will compile with those types. So it guesses everything on its own. So Numba actually does allow you the possibility to define specifically your own types for arguments. So if you want to ensure, for example, that your function has 2 floats as arguments, you can force that. But generally, it is better to let Numba figure this out on its own. And this actually saves you work because you don't have to specify the types. So let me show you a first simple problem just to demonstrate what kind of a speed up you can achieve. So I could have picked any problem, but one which I quite often use in my summer school courses. It's a problem from the Euler project, problem number 39. And the Euler project, you can find out more about it if you like. So the basic idea here is we are basically looking at triangles which have integer perimeter and integer sides and right angle triangles. So essentially we want triangles where a squared plus b squared equals c squared, and they're all integers. And then a plus b plus c are also integers. So it's kind of a math problem just to find integer triangles, so to speak. And for a particular value of p, there are various solutions. So for example, here for perimeter 120, there's 3 right angle triangles which have integer sides. And the idea is I want to write a program which checks triangles with perimeter up to 1000, and then find the value of p for which the number of these integer solutions is maximized. So to do this, I write a function which just has 2 nested loops where, so essentially it's kind of a brute force approach where I try all the possible values of a, all the possible values of b, and then c is just perimeter minus a minus b. I restrict my loops a little bit in that a cannot be greater than half the perimeter, and then b is generally greater than a in this convention I adopted. But fundamentally, though, we don't have to worry too much about the math behind the problem. Just understand that here I have a relatively simple Python code which just does 2 nested loops using default vanilla Python, nothing that interesting going on. And then when I run this code, I would run this for different values of p and find the maximum. So how do I convert this code into Numba? Well, first of all, clearly my code, this is really the only function which the code is running, so it's spending the most time in this function. So I'm going to put my decorator in front of this function. So I just do from Numba import njit, and here actually that's a typo, this should be njit. Although with JIT, this will also work because this is a code which compiles into Python, which Numba can compile without any issues. So whether you use NJIT or JIT, you'll get the same result. And with the Numba decorator, this code runs 273 times faster. So just by adding this simple decorator, I have speeded up my code 273 times. So this is an impressive number. You know, getting your, especially if you are doing production code, which will do many hours, you know, of computer time, getting your results 273 times faster will really speed up your, you know, your work. So it's really worth doing, and I think that's why Numba is something that everybody running Python code should be aware of and should be using it as much as possible, especially when you are doing time-consuming runs on our clusters. So this was a simple case, simple code, but in Python you have modules. I mean, Python is really dependent on modules. You rarely do things with just vanilla Python. So in order to actually speed up code which uses modules, Numba has to know about the module it's working with. So if your function contains some module that Numba is unaware of, putting the JIT decorator in front of it might actually even slow your code down because Numba just doesn't know what to do with the module. So for example, Numba does not know about pandas at all, about pandas module, at least currently doesn't. So any code which has pandas in it, it's might not benefit from using Numba. However, the good news is Numba is compatible with NumPy, and NumPy is the most popular mathematical module used very widely, and Numba can play along with it perfectly fine. So the next section of this talk, I will show you an example of a code which uses NumPy. So the example I use here is two-dimensional diffusion equation, and I am not going to go into the math behind this in the equation in any great detail, but the basic idea here is that I have some array, two-dimensional array U, which describes temperature or concentration of particles or something like this, the thing which is diffusing. And I have my concentration of particles in space evolving in time. So I want to have some kind of a time step algorithm where, given the configuration of the system at some time, I want to find the configuration at time one step forward, right? So I have an expression where the configuration in the future time is a UDT is expressed in terms of the configuration at the current time. And here I use the value of at point ij plus the neighboring values, because in diffusion I have second derivatives, and these terms here are just come from the discretizations of second derivatives on a grid. But the basic point is that I have loops and I use neighboring values. And then after I do all this, I have to have a copy step, because now the value I just computed, I want to, so this is a future time array, I want to copy its values to the current time array. And I have this function, and then I just evolve my system in time. So I have a loop where I call iterate as many times as I need to evolve the system in time. And here U is a NumPy array, in this case 1000 by 1000, and the UDT is the same kind of NumPy array with the same shape. So so this is my NumPy code. And even though NumPy is highly efficient as a numerical tool, in this case my code will run quite slowly because I have explicit loops. So I have a for loop and a for loop explicitly. And Python generally runs code like this quite slow. So what can I do? Well, the obvious thing is, let me try to add a Numba decorator in front of it and see how well it does. So all I do is I take exactly the same code I had before, and from Numba I import NJIT, and I put the NJIT decorator in front. And how much faster does this run? It runs 309 times faster. So again, that's a huge benefit. And we should definitely, I would say we should definitely use Numba then as much as possible, especially if you have a code which runs for a long time, because in the end, we just added this little line, and that's all we had to do. So there's no reason not to add this line. There's literally no penalty, at least in this case, to adding this line. Now, let's also consider, could we have, so Python should not be using loops. You want to, if you're working with NumPy, you want to avoid using loops. So just as a point of interest, let's look at a NumPy code which doesn't use loops and doesn't use Numba, but it takes advantage of NumPy features to basically do exactly what we did right now, except avoiding using loops. So essentially, we want to take this code, I just put it here as a comment, and we want to convert it to a code which doesn't use loops. Well, we know that if we are just, so the problem is, if we had only this in our expression, where basically we are adding, modifying an array element-wise, we wouldn't need those loops. We could have just said udt equals to fac times u, and NumPy would do everything element-wise, and the loops would be done implicitly. Now, the difficulty with this is we cannot do it because we have these I plus 1, I minus 1, j plus 1, j minus 1 factors. Our arrays are shifted by 1, so we have to account for this shifting. Well, it turns out that we can take care of this with proper slicing. So, so for example, here I'm going to update the, so here I'm going to update the interior of my array, not updating the boundary points. Note that here the loops are, they start from 1, they don't start from 0. So we don't update the element 0 simply because if we try to update with I equals to 0, then I minus 1 will be out of bounds. So we don't want that to happen. So, so what we can do is an array which gets access with I plus 1 and j, if we could just sort of shift this array by 1, if we could just shift it all over by 1, we could access that shifted array with just ij, right? And similarly here, if we could shift this array by 1 in the other direction, we could also access it with ij. And if everything is accessed with just ij without any plus 1 or minus 1, then I'm just adding a bunch of arrays. And for this, I don't need loops. So this shifting is precisely what I do here. So for example, here I have my array from element 1 to, and minus 1 means up to, but not including the last element. So if I want to shift this by 1 to the right, I'm going to start with 2, and then I'm just going to go to the end, including the last element as well. So I leave this blank, but this means I'm going to the end. And here, this is just j, so there's no shifting here. Similar here, minus 1. So with minus 1, I move 1 to the left, so I start from 0. And now I go up to, but not including the second last element. And the same thing happens for the j, for the second index in these lines, right? So here I have my iterate function where I update my array without any loops. So what this means in practice is underlying NumPy is compiled code. So when you call a NumPy routine, as long as it doesn't need to do an explicit loop, it actually calls compiled code underneath. So it's sort of similar to what Numba is doing. So I would expect my code to run quite fast. And in this case, I find out that it is indeed running faster. So it's running 157 times faster than Python with loops. So this will be another approach to speed up NumPy code. But notice that it's still about 2.0 times slower than Numba. So Numba still does better. So even though here I have got rid of the for loops, NumPy still has some limitations in how it can compile this data. So Numba is superior. It's also worth noting that could I have put, add JIT in front of this code? Sure. I mean, I could, but in fact, when I do this, it doesn't improve my performance. It actually slows it down a little bit. So when I put add njit, it's about 1.4 times slower. And of course, it's difficult to know exactly what is going on because I would have to look at the source code of Numba and all this, what it actually does. But my guess is here I am trying to compile code which is already compiled. So here NumPy is not using loops, so it's sort of using compiled code already. And in general, if you put compilation in front of compilation, it's actually not efficient. So anyway, what's the advantage of using this versus using this? I mean, first of all, as long as you're using one of these two methods, you're good. I mean, you definitely don't want to be running 100 times slower than you should be, right? but I guess it's a bit of a matter of taste. I mean, quantitatively speaking, Numba is faster in this case, so Numba should be used. And I think the Numba code is clearer because, you know, I think the +1 and -1, these clearly indicate that, you know, you're using neighboring variables to compute the value of at point ij. Whereas here, of course, it's the same thing happening, but the code is, I think it's a little bit less transparent. So of course, if you know NumPy, you'll know exactly what's happening and it will be obvious to you. But if you don't know NumPy, then this might be more confusing. But I would say both approaches are reasonable, but at least in this case, Numba seems to be doing better numerically. So, and I think it's of course easier because, I mean, it's only a single, we just had to add this. We didn't have to rewrite code like we had to do here. All right, so far I've shown you code where everything is working beautifully. You just add a single decorator line and then the code compiles. So is this always the case? Unfortunately not, because Numba doesn't support all of Python. It only supports a subset. So the Numba is under active development, so hopefully over time it will become better and better in covering more Python. But at least currently it supports only a subset, which means that if you're in a situation where you already have a Python code with, you know, hundreds of lines or thousands of lines, and you decide, okay, maybe I should try to compile it with Numba, it's quite likely that you will run into problems. That's because, you know, when you were writing your code, you were not aware of these issues. So you're probably using some code structures which Numba cannot deal with. So how do you get around this? Well, you have to fix your code. Like if you really want to use Numba, you have to modify your code in such a way that you avoid the features which Numba doesn't understand. And again, you don't have to change your whole code. You just have to focus on the functions where the code is spending the most of the time. So how difficult this will be, of course, it will highly depend on the code that you have. For some codes, it might be very easy. For some codes, it might be too hard. So I can't really tell a priori. So this is obviously a huge topic. I mean, you know, like to talk about all the features of Python not supported by Numba, that would take up too much time. So I picked just two examples which I have encountered when trying to accelerate the user code in the course of my work as an analyst, and this will just give you a flavor of what's involved in fixing these problems. So one particular problem area that Numba has are lists, because lists in Python can be very complex objects. You can have lists of lists, lists containing different types. And generally, Numba has trouble dealing with complex lists and complex list operations. So it can do lists, definitely, but the moment the list gets complicated or some operation gets complicated, Numba refuses to compile the code. And that's quite unfortunate because, of course, lists are ubiquitous in Python. You use them all the time. It's a very convenient object, and it has great methods associated with it. So how do we get around this? Well, the short answer is we want to replace lists with NumPy arrays because Numba deals very well with NumPy arrays. So as long as my list becomes a NumPy array, you avoid the problem. So clearly, this immediately restricts us to situations where your list contains values of the same type, right? I mean, if your list is mixing integers, floats, characters, then clearly you cannot proceed. So we are assuming that you're doing mathematics and your list contains similar entries. So so once we use a NumPy array instead of a list, we have to do the list operations as NumPy operations. So we have to translate our code somewhat to basically go from a list operation to a NumPy operation. So again, you don't have to convert your whole code. So one strategy you can adopt is once you get to the function which you want to use Numba on, you take your list, you convert it to a NumPy array, you feed this as an argument to your function using Numba, and then once you are done with it, you convert your NumPy array back to a list, and then your code just proceeds doing the other things. So this is good because you can still use the list operations in the places where the code doesn't spend a lot of time, and you only have to do the conversion in the places where it spends a lot of time. So let's look at our first example. So Deepcopy has an issue with Numba. So this is unfortunate. So copying a list in Python is a tricky proposition because a list can be a very complex object. So the function which guarantees that the list is copied fully and completely in Python is Deepcopy. So let's say here I call a function where I provide some list A, and I want to make a copy of this list, create a brand new list B, and here I just modify its entry and I return it. So very simple code. And when I call this function with a decorator, unfortunately, Numba does not compile this. Numba just doesn't like Deepcopy. It cannot deal with Deepcopy. So that's an issue. How do we get around it? Well, we convert it to a NumPy array, we copy that, and then we convert back to a list. So that's the approach. So here, this is the same code. Here I define my list here, and I convert this list to a NumPy array. So the operation here is very simple. It's just np array, provide the list as an argument, and this will return A, which is now a NumPy array. And I call my function. And inside my function, I take as argument A, and I use the NumPy way to copy an array, which is np.copy method. So this will take array A and will produce array B. I modify this entry of the array just to do something to it, and I return B. And at the end of this, I can convert this array back to a list. So of course, a code like this is a toy code. You would actually never do this in real life. But the point is, if you have some long function which you're converting to NumPy, and this function contains a deep copy operation, you want to replace this with a NumPy copy operation. So, and this will be our general strategy with dealing with lists. Always convert this to a NumPy array first before you deal with it. Okay, let's look at a more complex example, and this one involves filtering a list. So, so let's imagine that we have a conventional Python list which contains lists. So we have a list of lists. So we can think of this as X, Y, Z coordinates or whatever you want. So we have a list of sublists where we have a sublist 111, 909, 999, 234. And I want to filter this list so it doesn't contain any 999 entries. I want to remove that. So the conventional Python provides a filter method for lists, where the way this works is I call a list while I supply a filter, and a filter is a function, lambda function in this case, where just this function takes the value, successive values of A, so successive sublists. And if that sublist is not equal to 999, then it returns true, and otherwise it returns false. So once we have this array of true and false, the filter works on this, and for the element in which this returns true, the element is kept. For the element for which it is false, it is not kept. So when you run this, you have we have our original list, except the 999 element is gone. And you can imagine that this is something quite convenient to do in all kinds of situations. You just want to filter out some data. But you can imagine that this is not an easy operation, because here we have a list comparison, right? So we have X is a list itself. So how do you make sure that a list is not equal to a list? Well, you have to go element by element, and you have to compare. So even though this code is very compact, it is actually doing a lot of stuff. So let's say I write a function and I try to put the Numba decorator in front of it. So I'm just trying to do this filter. And Numba will refuse to do it. It gives me a warning and it says type error. So it's basically, it is uncomfortable with dealing with lists of lists. There's some deep reasons why it doesn't really know how to handle this situation. Interestingly enough, if you have just a list of normal types, so not lists, but integers or floats, the Numba will be able to cope with it, though you will get a warning. It will warn you that there's some possible deprecation in the code. So Numba is trying to come up with a new way of dealing with these kinds of situations, and in future versions, it might be better at it, but currently it just cannot cope well with this kind of a filter operation. And that's just a big caveat on this entire talk. Like if you're watching this talk recorded a year from now, Numba might have added some new functionality which makes this kind of a problem go away. So this might become outdated in the future. Okay, so even though this code is quite convenient, it doesn't work. So what do I do? And here, unfortunately, there is no trivial solution. I can't just magically change some keyword and get this working correctly. I have to get more creative. So in particular, I will have to use NumPy logical operations. So so let's, in this case, consider the same list that we had before, and I'm going to convert it to a NumPy array. And here I'm printing out this NumPy array. So again, it's the same numbers, but because it's a two-dimensional array, it's just printed out in a slightly different format. And I want to get this array, the final answer, where 9, 9, 9, and 3 is removed, right? So the basic reason why I cannot do it very simply is NumPy doesn't have a good array comparison functions. I can't just compare a whole array with another whole array. That would work in this case. So I have to get a little bit creative using logical operations. So this is gonna get a bit complex. So if this is not obvious to you, you might want to spend a little bit more time after the talk reading up how logical operations work. But here's a basic idea. Let's just focus on this. So this is a slice. So this is a slice where I make a NumPy array which contains only the first element of this list. So this is going to be, this array would contain 1, 9, 9, 2. And then I put a logical expression here, not equal to 9. So this expression will basically check whether the value of this new array I created is not equal to 9. If it's not equal to 9, it will return true. Otherwise, it will return false. So this is really an array of true falses, right? So this returns true when the number is not 9 and not true if the number is 9. So and here is another array where I do the same thing. So this is an array of true and false, except now I look at this value, right? And then I apply an OR operation to these to get a new arrays of true and false. So the OR operation works like this. If I have true, true, that returns true. If I have true, false, returns true. False, true, returns true. And only false, false will return a false, right? So so this is a logical OR. So as long as one of the elements is not -9, this will return true. That's the basic idea. And then, well, I have 3 coordinates, so I have to put this, I have to do an OR operation with another array of true and falses, which deals with the last coordinate, right? So this is a whole array of true and falses, right? And I now apply a logical OR to this, to both this and this. And this will give me the final array of true and falses, which returns true if one of the elements is not a 9. So it will return true for this, true for this, true for this, and this will return false for this. And then finally, this whole thing, this whole array of true and falses is sitting as an argument of the NumPy array. And this is exactly how a NumPy array applies a filter. So if you have a NumPy array and you supply a Boolean array as an argument, the new resulting argument will have only those values for which the corresponding elements in the Boolean array here are true. So this is how filtering is accomplished. And even though I have a two-dimensional array, this will apply this filtering to individual triplets. So, so some triplets will be kept and some triplets will not be. And here I print the filtered value. So is there a simpler way to do it? I couldn't actually think of one. Maybe somebody who knows these kinds of operations better than I do can think of a simpler way, but this at least works. And this applies NumPy operations. There's no loops or anything like this, so everything should be working pretty quickly. So the final code, which just uses what I have shown you here, is again import NumPy as NP, import njit, and then I define my apply filter function where I have my NumPy array A, and I apply the logical filter, and this returns the filtered value. And if I would have run this, this would have returned at the end a list which doesn't have 999 in it. So in the code, what I would do is, starting with a list, I would convert it to a NumPy array. apply filter to the NumPy array, get a new NumPy array, and convert all of this back to a list, and then proceed to do something else. So again, these are simple examples. The point is not to suggest that you would actually have a function which only does this. Rather, consider a situation where you have a big function which does many things, and one of the things it does in particular is apply this kind of filtering. And then you have to basically fix that line to get Numba to compile your code. So, so I don't know what your impression of this is, whether this is simple stuff or difficult stuff. Again, everybody's code will vary, so the level of difficulty involved in fixing your code will vary as well. Now, it's really pointed out that here we are analysts at the Alliance, so we are here to help our users. So if you want to convert your code to use Numba and you run into problems, definitely submit a problem ticket, and we will try to help you figure it out. And I would say that if you are running anything significant that will consume, thousands of core hours on our clusters, you really are obligated to look into this kind of code acceleration. I mean, it's going to be great for your research because you'll get an answer 100 times faster, which is surely very nice, but it will also make sure that our clusters are used efficiently. So the last slide, let me just mention some other features of Numba. So I barely scratched the surface. There's other things that Numba provides, other interesting things that you can do. For example, it provides automatic parallelization. So just like we only had to add NJIT to get our code running faster, if everything goes well, you just need to add parallel true to make your code running even faster by using multi-core parallelization. But this is nowhere near as straightforward as just using NJIT, because NJIT is guaranteed to give you correct code, basically. Like, as long as it compiles the code, it's guaranteed to be correct. With parallel, it's not true. With parallel code, it's now your responsibility as a programmer to ensure that the code that you actually give Numba to parallelize is actually parallelizable. And if it is not, then you might actually get wrong results. So it's a pretty complicated topic, and that will require a long discussion, but at least that possibility does exist. You can, in theory, speed up at least simple loops with just a single keyword like this. Another possibility is it is possible to compile your code for the GPU. The syntax for this is somewhat more involved. It is no longer enough to just specify NJIT. You actually have to modify your code to specify how you're going to decompose your loops into using multi-threading, and how these threads and then these threads get run on the GPU. So it's not super complex, but it is definitely a different level of complexity than just adding a simple decorator. And if you're interested in this kind of thing, we will be covering high performance computing with Python at the Compute Ontario Summer School. So the Compute Ontario Summer School is actually going on right now. It's going on for a few months with weekly courses. The HPC for Python will be covered in the last week of June. And if you're interested, this is the link which you can go to and register for that. So that's it. I'll stop here.